Okay, guys, so I'll show you how to do that same example, logistic regression, with the hours studied, except on a neural network this time. So here, X, our input, is going to be hours studied. So we'll just call that input 1. And this will be a super simple neural network. So we're going to have a weight here. We're going to have a bias here. And we're going to have an activation function, sigma 1. Let's call this hidden layer. Oh, wait, this will just be the output. Yeah, sorry, this will be a ridiculously simple neural network. So this will just be output. And we're just going to output via some activation function, sigma 2. Okay, now for the task that, remember we were doing logistic regression from the previous video with 20 data points. For hours studied versus past probability. You can pause the video here and see if you can tell me what sigma 1 and sigma 2 are. And also, if you want also, let's do this in green. See if you can figure out what this B1 translated to in the previous video and what this W1 translated to. So you can pause the video here. Okay, so sigma 1, well, first of all, yeah, let's do W1 first. So W1 plays the role of B. That's the sharpness of the logistic curve. And B1 plays the role of A. Because remember that we want 1 over 1 plus e to the minus a plus bx. So if we look at what the edge from I1 to O1 does, that output will be W1 I1 plus B1, which in this framework, that'll tell you that that'll look like A plus BX. So actually, this will be negative B and this negative A, but it doesn't matter. At the end, your optimization is going to figure that out anyway. So if we have W1 I1 plus B1, that means that sigma 1 is just the identity. And the identity is just a function I such that it just outputs. It doesn't change anything. So going into O1, we just have that linear combination. And then sigma 2 of x is 1 over 1 plus... Actually, no. Yes, it won't be negative b. Sorry about that. Is just this. So in total, our neural network does the following. It computes what is 1 plus e to the minus a plus bx. And then you would do your normal back propagation stuff with the loss function minus L equals minus the sum I equals 1 to 20. Yi log pi plus 1 minus yi log 1 minus pi. And that's it. So that optimization is the same. It's the magic that I did, or that Wikipedia did for me, but that code can do for you to get those values. So if you ran a neural network, if you used PyTorch or something like that, it'd be equivalent to whatever Wikipedia did, whatever algorithm they used to find the A and B that minimize this. So that's a cool example where you can see the a classical method and how it translates to a simple neural network. Now, I guess as another motivator for how this fits into machine learning, now you can imagine that we input a bunch of these. We do some complicated task. Let's do a different color to show. We do some complicated task. And then so on, and we have tons of hidden layers. This activation function is logistic. And then this one is logistic. And then this one is logistic. And so on until you get the output. Output 1, output 2, and so on. So then what this does basically is you can think about a logistic function as basically making fuzzy decisions for you. Because remember that this is a hard decision for the perceptron. This says 0, 1. There's no fuzziness to it. But this gives me some fuzziness here. I'm not entirely sure whether it's 1 or 0, but I have a pretty good idea. Now you can imagine stacking all of these onto each other. If the logistic function is all throughout this neural network that has thousands of nodes, you're making a bunch of probabilistic statements that because the data doesn't tell you everything. So that's really where you're going with logistic regression and why that's typically covered at the start of a machine learning course. I hope you liked the video, and let me know if there's anything that confuses you. Thanks.